morning and good afternoon, good evening, everyone, depending on where you're attending this from. So welcome to the third presentation in this Cryoscope monthly webinar series, where we will showcase scientific advances from our project. So my name is Mariam Younes. I'm a communication manager at Revolve, and I'm responsible for the communication and dissemination of the Cryoscope project. I will be moderating today's meeting. So Cryoscope, for those who don't know yet, is a Horizon Europe Research and Innovation Action project aimed at understanding physical and chemical processes within the coupled cryosphere, atmosphere, hydrosphere system across core regions in Europe and India. The project brings together 20 partners across 9 countries, and it is co-funded by the European Union, the Swiss State Secretariat for Education, Research and Innovation, and the Indian Ministry of Earth Sciences. So I have the pleasure of introducing today's speaker, who is Dr. Harsh Beria. Dr. Harsh is a research scientist at ETH Zurich and the WSL Institute for Snow and Avalanche Research, SLF. He holds a PhD in environmental sciences from the University of Lausanne in Switzerland, and he is the scientific coordinator of the Cryoscope project. Harsh's research focuses on understanding how water moves through natural landscapes, from its arrival as rain or snow to its emergence in streams. Harsh is also developing the first future snow scenarios for Switzerland in the Santa project, which is a joint project between the SLF and Meteo Swiss. So today, Harsh will give us a talk about where does the snow go, tracking snow losses from air to streams. And he will present ongoing work to quantify snow sublimation losses across snow-influenced regions of the Northern Hemisphere. The schedule of the talk is around 40 to 45 minutes, and we have 15 to 20 minutes of Q&A questions and answers. Also, if you have any questions during the talk, you can raise your hand or you can send your questions in the chat. And after this, we have like 20 minutes for discussion questions, where we can also raise your hand. So I give you admission to speak, or you can just write your question in the chat. So thanks a lot, Harsh, for giving this presentation, and I hand you over the stage.
Yeah. Hi, everyone. Thanks, Mariam, for the very kind introduction. So in today's presentation, I'll be talking about some of the research we are conducting in Cryoscope. One of them is on quantifying snow sublimation losses, and the other one, which we are leading, is trying to understand how stable water isotopes in different hydrological fluxes can teach us more about hydrological process understanding. I have broken down this presentation into 2 parts. The first is on quantifying snow sublimation losses in our sublimation related work. And the second part, I'll be talking about our isotope based research. I'll take a break in the middle to also take questions, and then we can take it from there. The first part of the presentation is to try to quantify how much snow gets lost via sublimation. So sublimation is a direct loss of snow via vapor. This typically happens during the winter periods when the ground is snow covered, and any moisture which is lost to sublimation cannot contribute to meltwater. So higher sublimation would imply lower spring meltwater availability, which has implications for downstream water resources. There have been interest in quantifying snow sublimation for a very long time. However, there is no clear agreement on how much snow gets sublimated. On this table, on the right of this figure, there was an attempt to quantify how much snow gets sublimated from a metadata compilation of different studies, but the estimates are very huge, with some studies arguing that sublimation can range between 5 to 90% of winter snowfall, which basically means we do not have a very good grip on how much sublimation actually happens. There have been global compilations showing values of snow mass of 0.2 to 6 millimeter per day being sublimated, and these are very huge ranges. Together with a colleague, Adria Fontrodana Bach, who's also working on this topic, we tried to produce what do models think in terms of how important is sublimation to the total ablation. Here, total snow ablation is expressed as sublimation plus snowmelt. So this is all the water that is available via the snowpack. And here we try to quantify how much surface sublimation contributes to total snow ablation using ERA5 land reanalysis. We see very clear hotspots in Antarctica, in the peninsula region of Antarctica, in eastern Siberia. We also see hotspots along Greenland. We also see hotspots in the western US. However, this really comes from the modeling perspective, where we do not really have a strong grip how reliable these models are, because ERA 5 land itself is it's run using ERA 5, which is run at about 30 to 40 kilometer resolution, at which complex topography cannot be resolved. Um, so we also tried to put in together more observations in terms of flux towers to identify sublimation hotspots. So this is just a depiction of hotspots of sublimation with ERA 5 land. We also see that High Mountain Asia is another region where we do not have many observations, but it seems to be an emerging hotspot. We also see hotspots in the western US and eastern Siberia. So, how do we actually measure sublimation? Because we wanted to see if our hotspot analysis with ERA 5 land um, is accurate. So, conventionally, there are four methods to estimate sublimation. Eddy covariance is the most direct way, where we measure wind speed and water vapor at 10 to 20 hertz frequency, and then using boundary layer process understanding, we try to estimate how much latent heat flux losses go in the upward direction, which would be away from the snowpack, so sublimation. There have also been attempts to use gravimetric measurements. These tend to be very local and cannot be scaled, because installing very large snow lysimeters is mostly not feasible in remote regions. There are other approaches such as the Bowen ratio, energy balance, bulk aerodynamic flux, and aerodynamic profile. There was a there was a paper from colleagues, Sexton and colleagues in 2016, where they tried to benchmark these different methods at a single site in the Colorado Rocky Mountains. And they reported that eddy covariance method has the most accurate depiction of sublimation, and they benchmarked eddy covariance with other methods. So we do have a lot of eddy covariance data, especially because a lot of carbon flux community measure these eddy covariance fluxes to try to estimate carbon sequestration in diverse regions. So in this study, we tried to compile a lot of different flux tower data, which is already available. So trying to compile networks such as FluxNet, Ameriflux, ICOS. This results in about 550 plus sites globally, where carbon and water fluxes are measured at 10 to 20 hertz frequency, and latent heat fluxes are estimated at 30-minute intervals. These sites typically also have measurements of four-component surface energy balance, which includes both short-wave and long-wave incoming, outgoing radiation. And in this study, we tried to put together a global network of all these flux towers. So this was done with a colleague from IIT Kharagpur, Professor Ankit Shekhar. So out of these 550 plus sites, we were able to identify about 104 locations spread across the Northern Hemisphere, where we had at least 3 winters of latent heat flux measurements. You can see that there are a lot more sites in Western Europe, in North America. There are no sites in high mountain Asia. Also, very few sites in higher latitudes. Uh, Interestingly, we have about 34 locations which have more than 10 years of data. So if you wanted to do some climate time series analysis, this kind of a data set would be very useful to try to do this. So as these sites are largely used for ecosystem monitoring, and ecologists are more interested in growing season during summer and not so much interested in winter. So at most of these sites, we do not have measurements of snow depth or snow water equivalent. So we had to try to estimate when the ground is becomes snow covered, because we only wanted to attribute latent heat fluxes when the ground is snow covered to have an accurate depiction of snow sublimation. So we created a small methodology where we were using albedo measurements at all these sites, because we can write albedo as a ratio of outgoing to incoming short wave radiation, and snow typically has a very high albedo. So here I show daily albedo values for two example sites, one in the US, one in Finland. And you can see that the albedo values are shown in light gray color, and the albedo values vary quite a lot between years and also across sites. So we couldn't just say that if our albedo is greater than zero point 0.3, it's snow covered, or if it's greater than 0.6, it's snow covered, because we have lots of interannual variability and site specific variability in albedo. So what we tried to do here was fit a do a low pass filter expressed as a moving average over 360 days, and we said that any dot which lies above this 360-day moving average, which is shown in green, as a good depiction of the ground being snow covered, whereas all the points below this are we do not know if they are snow covered or not. So we only express sublimation or estimate sublimation values for parts of the year when the albedo values are quite high. So with this kind of a methodology, we try to estimate how much sublimation contributes to the annual evapotranspiration. So how much winter latent heat fluxes are a function of annual latent heat fluxes. And please mind, we are talking about latent heat fluxes in the upward direction, because at nighttime or in early morning, we also have condensation, which is in downward direction. So we were looking at upward direction losses of sublimation typically happening during day. And across these 104 locations, the average sublimation loss as a percentage of annual ET is about 7.5%. We see very clear hotspots. For example, Western US again comes out as a hotspot, which we also saw in our ERA 5 land reanalysis. We also see that we have about 10% of ET being lost to sublimation in the European Alps. We have a huge data void in high mountain Asia. Now, if we express sublimation as a percentage of annual precipitation, so instead of normalizing sublimation with annual ET, here we are trying to normalize sublimation with annual precipitation to quantify how much of the water balance is lost via sublimation. And here the picture changes a little bit. So the sublimation as a percentage of annual precipitation is a bit lower, about 4.7 percentage. And over the European Alps, we typically see much lower sublimation values. This is also because the European Alps receive precipitation throughout the year, whereas in regions in the Western US, they receive most of their precipitation during winter. So when we have precipitation during summer, this would be lost to evapotranspiration and not to sublimation. And this is also why we have lower sublimation fluxes in the Alps and much higher sublimation contribution, going up to 20% of the annual water balance. Average across sites, this number is about 4.7%. So in the beginning of the presentation, I had mentioned that about 5 to 90% of winter snowfall gets lost to sublimation. We were really able to come up with a more precise number, at least at these 104 locations. And our estimates show that sublimation is towards the lower end of this range and not towards the higher end of the range. Whereas there are locations where sublimation can remove up to 20% of precipitation, but they are largely located in few regions. This is also a limitation of the data set we have because we do not have a lot of data set in eastern Siberia or the high mountain Asia, which also emerged as hotspots of sublimation. If we look at how sublimation varies across different land uses, we typically see that there's higher sublimation in land cover, which are described as snow and ice, shrublands, evergreen needle forest, and woody savanna. So typically, our main takeaway is higher energy systems or forested systems, or at least evergreen forest. They have higher sublimation. This has also been reported in literature in a few studies where evergreen needle leaf forests have a higher sublimation contribution because they also intercept a lot of snowfall, and it's much easier to sublimate the snowpack from intercepted snow than snow on the ground. So we also try to benchmark four existing Earth system models and try to compare how our sublimation estimates compare with these models. The picture is a bit grim. Uh, Almost two of the models, GLDAS and Gleam, they had barely any correlation, and these are correlation on an annual time scale. So we are calculating our annual sublimation at our flux tower and at the same grid from the model. Although it's not a complete like-to-like comparison because the model resolution is in the order of kilometers, whereas the footprint of a flux tower is in the order of hundreds of meters. So there is a resolution mismatch. However, that resolution mismatch still doesn't explain why the models do not do a very good job at simulating sublimation. We also saw that GLDAS, in some scenarios, they even simulated negative sublimation on an annual basis. What that means is uh, uh, condensation exceeds sublimation, which we have flux towers also in deep Antarctic, and even there in such dry landscapes, we see that sublimation still exceeds condensation. So we are not really sure if these models are getting their boundary layer dynamics incorrect. Era 5 land emerged as the most reliable of the four models, which simulated surface snow sublimation. However, the Era 5 land had a clear bias in years with high sublimation, where Era 5 land systematically was underestimating sublimation fluxes. So now we moved a little bit to trying to identify drivers of sublimation at a single site in the Swiss Alps. So we now try to develop a method. We try to develop a methodology to estimate what are the key meteorological drivers of sublimation, to then see in our correlation graphs with models where we were seeing that Earth system models are not really doing a very good job. We want to see what sensitivities are they missing. So we try to first do a sensitivity analysis or to quantify drivers of sublimation at a single location, Weißflöck in the Swiss Alps. So Weißflöck is located on the eastern part of the Swiss Alps. It's one of the oldest snow monitoring sites with gauging going back to 1936. We had a new eddy covariance flux tower installed in 2024 in collaboration with the Snow Processes Group at SLF. And this work was led by our master student, Isabella Anglin, who did a master thesis on drivers of sublimation here. You can here nicely see how the footprint of the flux tower also changes according to different wind conditions. So at this location, we try to quantify sublimation over an entire winter, which has not been done before in the Swiss Alps. So we have campaign measurements of a few days to quantify snow sublimation losses, but never over the entire winter period. So for the 2024-25 winter, we tried with this new eddy covariance flux tower, we estimated cumulative sublimation at about 25 millimeter, or it was about 5% of peak winter snow water equivalent. So kind of in range, in line with our global estimates as well. What was very interesting for us was that the distribution of sublimation between the accumulation and the ablation seasons were very uniform. So almost half of sublimation happened during the snow accumulation season, and half of sublimation happened during the snow ablation season. This is particularly important because the accumulation season, which ranges from November to end of March, is much longer than the ablation season, which where the snow melts from April to end of May in this case. So the average sublimation rate was much higher, or double, during the ablation period versus the accumulation period. And this might have interesting dynamics for future snow sublimation losses as the melting period, or the period of snow melt, either expands or contracts. There is no clear agreement within the community if the melt period becomes longer, because if it becomes longer, then we probably have more sublimation. If it becomes shorter, we'll probably have less sublimation. So that's something interesting. We found that sublimation was much more important during the ablation period than during the accumulation period. We also tried to quantify what are the key drivers or statistical drivers of sublimation with partial correlation analysis. We picked a big range of variables which were reported in literature, and in the end, we found that vapor pressure gradient and wind speed were the most robust statistical controls on sublimation, whereas also shortwave radiation, which we did not expect, was accounted for some part of sublimation losses. Snow surface temperature or air temperature were not really independent statistical controls. We also did a machine learning based analysis of sublimation sensitivity with something called the SHAP analysis, which uses the concept of game theory and tries to estimate the sensitivity of an output flux to its inputs. In this case, our output flux is sublimation, and the input flux is our vapor pressure gradient, wind speed, snow surface temperature, and net shortwave radiation. So with this kind of an analysis, we can quantify what is the importance of individual atmospheric drivers during different periods of the year. We see very nicely that the yellow lines are only visible during the melt period, and the yellow lines depict sensitivity with shortwave incoming radiation, whereas the yellow line was not as visible during the accumulation period, which also tells us that shortwave radiation is more important during the ablation period when we have much more shortwave radiation. We also were able to do a full sensitivity analysis across the parameter ranges, and we nicely saw that in vapor pressure gradient, negative vapor pressure gradient actually decreased sublimation, or another way, it increases condensation, because at night time when the atmosphere becomes saturated, we have water vapor transport from the atmosphere to the snowpack. And we saw this nice nonlinear relationship with vapor pressure gradient. With wind speed, we saw mostly a linear relationship, with higher wind speeds contributing to higher sublimation rates, which also makes sense, because that's how more wind speed would increase the extent of turbulence. And sublimation is physically expressed as the multiplication of wind speed and vapor pressure gradient. Snow surface temperature itself was an important throughout its range. This is particularly interesting because there have been papers in literature showing that snow surface temperature has some control on sublimation. What we realized in this study was snow surface temperature controls sublimation through vapor pressure gradient, because snow surface temperature directly controls the vapor pressure within a snowpack. So its effect is more indirect via vapor pressure gradient. And once we account for vapor pressure gradient, snow surface temperature itself is not as important. The very counterintuitive result which we found was at high shortwave radiations, we saw positive sensitivities of sublimation. So higher shortwave radiation increasing sublimation. This is a process which we are still trying to investigate. What would be the physical control of this? Because in principle, shortwave radiation should make the atmosphere more drier. So its effect should be captured in vapor pressure gradient. In this analysis, what we see is above a certain threshold, the effects of shortwave radiation are not carried to vapor pressure gradient. So this is something which we will continue investigating. To the last part of this snow sublimation presentation, I'll also show you some of the early works on trying to quantify the changes introduced in the snowpack due to sublimation fluxes. So during 2025, Isabella Anglin also conducted many campaigns to Weissflioc, where she was measuring isotopes in the first centimeter of the snowpack, 1 to 2, 2 to 5, 5 to 8, and 8 to 11. So very high resolution uh, characterization of snowpack isotopes, and she was doing 5 different bits every day whenever she went. And what was interesting for us, so this is period from March to end of April 2025. What was interesting for us was with our eddy covariance system, we saw that this was the period when we saw a lot of sublimation fluxes in our measurements. And this is the period when we also saw the expected changes in isotopes, which we would expect from a physical process where our O18 isotopes in the top layer of the snowpack becomes more enriched and the DXS values decrease. And this is like a classical signature of sublimation. Uh, uh, I'll just show you from a physics perspective what we actually expect. So, if the snow lies on this local meteoric waterline, snow sublimation would enrich the remaining snowpack along this line. And this is also what we see on a few days with high sublimation rates, where our initial snowpack isotope samples collected early morning were along the line, but during the day from 8 to 11, 2 p.m. and then 5 p.m. they went along this snow sublimation line. So this is really like I cherry picked a date where it actually worked, and there are lots of dates where it also doesn't work as well. But this is something we will continue working on over the next year. So now we move to the next part of the presentation, which is on trying to advance snow hydrology by using stable water isotopes. This work was particularly done with Lionel Benoit, who's a scientist in Ra in France, and the most of the field work was organized by Nathalie Seppele and Bettina Schaffli's group. So I would like to call out my co-authors on this work. So before going into isotope-enabled modeling, I wanted to quickly give a background of isotope hydrology. Uh, so a water molecule is made of two atoms of hydrogen, one atom of oxygen, and the most prominent state of hydrogen atom is the H1 state, and for oxygen it's O16. So for every million molecules of water which has only 1 and 16 of hydrogen and oxygen, we have about 1880 to 2000 isotopal logs with O18 and 180 to 340 isotopal logs of H2. So these small differences in atomic mass can be used to can be detected with mass spectrometry or laser mass spectrometry. So there has been a huge development in the last 15 years with the evolution of Picaro machines, where they are able to do this mass spectrometry with lasers to make it much faster. So very small differences in atomic weights can be used to infer the proportion of O16, O17, O18, H1, H2, H3. So to quantify heavy versus light isotopes. Just some background basics on isotopes. So we typically assume that the ocean water has a isotopic composition of 0, just as a baseline, and the vapor that evaporates from the water, the vapor always can the lighter isotopes get evaporated more easily. So they make the remaining water a bit heavier, but the vapor itself becomes lighter. So you see that ocean has an O18 of 0 per mil, and vapor has a negative, so it's lighter than ocean water. And then whenever we have condensation, the heavier stuff gets out first, making the vapor even lighter. So when we see that the vapor goes from minus 13 to minus 15 after a rain shower, and then even more negative. So the idea is evaporation takes away the lighter isotopes, condensation deposits the heavier isotopes. People have also shown that precipitation isotopes are strongly correlated with air temperature, where higher air temperature leads to larger isotopic values or isotopic ratios. Lower air temperature correlates with lower isotopic values, and this has to do with cloud condensation temperature. At what temperature the condensate was formed within the cloud, which is strongly related to air temperature, and that's why there's a strong relationship between air temperature and isotopes. But what this allows us is to detect signatures of snow versus rain, because we typically have snow in winters and rain during summers, and summer temperatures are much warmer. So the isotopes during precipitation isotopes during summer are also heavier, or they have higher values, whereas winter isotopes or snow isotopes have lighter values because winter temperatures are lower. Uh, we also see this in our GNIP network of stations in Switzerland, where our summer isotopes are have much higher values than our winter isotopes, and this is true for both deuterium isotopes and OAT values. And this then allows us to, because we are getting two different end members, so our rain isotopes, which takes higher values than our snow isotopes, and everything else we measure lies somewhere in the middle. So we can always try to quantify how much of my stream water comes from snowfall versus rainfall, depending on how close this cluster of points is with either this cluster or this cluster. So that's a little bit of methodology background on isotope hydrology, and we also showed in a conceptual diagram a decade ago that isotopes can help us track the hydrological cycle. So we kind of know how each process affect the isotopic composition of the remaining water and the vapor. So in principle, we can use stable water isotopes to track the hydrological cycle. So with that background, I will now take you to another alpine catchment in southwestern Switzerland. This is close to Lake Geneva. The catchment is called Valendino. It's a small headwater catchment, about 13.4 square kilometer. It has a very sharp terrain, going from 1,200 meters at the outlet to about 3,000 meters in top of the catchment, where there is also a small glacier. This is a protected catchment, so there are no reservoirs. The only human activities there are people going up for hikes and sometimes some Swiss cows. Uh, and we had organized a lot of data campaigns from 2017 to 2019, where we tried to collect stream water every 6 hours, and then we were sampling the other components of the hydrological cycle on a bi-weekly basis. Just to give you an overview of the stream flow generation dynamics in this catchment, we go from a we go from a very steady state, low flow conditions to very high turbid flows in a matter of an hour and a half. And if you're there, you actually see it, where an hour before you are like roaming around, and it's a very nice sunny day, and in an hour or so, you have boulders coming down. So it's a very flashy catchment where stream flow response to rainfall can happen with less than an hour. With a new technique called ensemble rainfall runoff analysis developed by James Kirshner, you can scan this code to the relevant paper. We were able to quantify how quickly our stream responds to rainfall events. And in the case of Valendino, we see that our stream flow, peak of stream flow response happens within an hour of rainfall. So it's a very flashy kind of a catchment. Over the 2 years, of our high intensity monitoring period, I would like to show you how the stream flow and stream flow isotopic ratios changed. So streamflow is shown on this graph, and streamflow isotopes are shown on the above graphs. The rainfall isotopic signature are shown in the violet bands. The groundwater isotopes are shown in green bands. And a few things which shoot out or are very prominent in the 2 years is whenever we were able to measure our stream water during a rainfall, we saw that our stream water isotopes also showed a similar response to stream flow, although much more damped responses. And we saw this in both years. I've just highlighted some events for you to visualize a little bit. We would for this study, we are trying to model both the streamflow response behavior and the streamflow isotopic response behavior using a new hydrological model which we developed here. So it's a simple rainfall runoff model based on geomorphological unit hydrographs, where the spatially distributed rainfall is simulated with an initial abstraction step to generate direct flow. So the rainfall, which actually becomes runoff very quickly, so in the order of 15 minutes to an hour, and how this rainfall then infiltrates into our groundwater storage and how that mobilizes our groundwater flow generated from groundwater. So the GIUH based geomorphological unit hydrograph is spatially distributed, whereas our groundwater representation is spatially lumped in this case. And because we did only spatial distribution on our surface runoff, we were able to speed this model up significantly. Whereas if we wanted to do also the lateral transport in groundwater, it becomes very, very computationally expensive very quickly. We also have a small snow model integrated in the system. And with this kind of a model structure, we try to estimate both streamflow and streamflow isotopes. So here I would now show you some results from a split calibration test. So we had two summers of measurements. What we tried to do was calibrate on one year and validate on the other year and vice versa. So we once calibrated just with 2017 data and validated with 2018. And then we calibrated with only 2018 and then validated with 2017. So a split calibration strategy. We calibrated our model just based on streamflow values and also based on streamflow and streamflow isotopic values. The one thing to call out here is the model was run at 10-minute time steps because we wanted to capture the high resolution responses. So it's run at a very high resolution. So here are some results. Whatever I show here are just the validation results. So a bit more honest, maybe. So here with streamflow calibration, I'm trying to show how do our streamflow isotope calculations look like. And we actually see just with streamflow calibration, our error bands, which show the posterior of our model simulations, they already capture most of our observed streamflow isotopic values. So the observed streamflow isotopic values are shown in black dots, whereas the model simulations are the light gray line in the background. So just with just with streamflow calibration, our model achieved reasonable simulations of streamflow isotopes with Nash-Sutcliffe of 0.3 in one year and 0.6 in the other year. But more importantly, there was no real bias. So the biases were always below 1 per mil. With an additional isotope calibration, we were able to further improve the model. The clear improvement we see is the bands in the top two graphs are thicker than the bands in the bottom two graphs. So we were able to reduce the uncertainty in our simulation significantly, and we also gained some skill in terms of hydrological evaluation metrics for streamflow isotopes. We'd also now show you what did our calibration strategy, how did that impact streamflow itself? So this is for 2017. So now the discharge calibration is shown on the left, and the discharge plus isotope calibration is shown on the right. So you can compare. So with isotopic calibration, in one year, we were able to even improve our discharge simulation with better Nash-Sutcliffe values, lower biases, and lower errors. In the other year, we lost a bit of skill in discharge simulation, where our Nash-Sutcliffe reduced a little bit. But more importantly, what we realized was with our isotope calibration, which is shown here, we were able to better capture floods. So our model simulations without isotopic calibration had huge overestimation of floods, whereas our model calibration with isotopes had a better representation of flood processes. So if I now take you into how the different fluxes are partitioned. So I'm now trying to simplify it into three main fluxes. So direct flow, which is your rainfall directly going to runoff with a time lag, snowmelt, and groundwater. Irrespective of the calibration strategy we used, we noticed that even in such a flashy catchment, more than 80% of summer stream flow is generated by groundwater, which is a particular surprise because if you are actually in the catchment, seeing such turbid flow, you would imagine that it's the rain falling right now which is mobilizing such a big runoff. Whereas in our case, we really showed with isotopic modeling that even in this kind of a system, most of the stream flow is actually modulated by groundwater. We also see that in isotopic calibration, our error bands are a bit smaller, so we get better parameterization of the different fluxes in all the 3 years. So from this part of the presentation, I want to highlight the key takeaways, which is groundwater dominates stream flow generation, even in very flashy alpine catchments and even during peak flood events. And calibration with stream isotopes reduces parameter uncertainty. And also our simulations show that less than 10% of a direct runoff is generated even in such a flashy catchment. So the entire system is groundwater modulated. And isotope informed calibration yields sharper and more robust flux partitioning. I think with that, I see my clock and I'm already at 39 minutes. So now it would be a good time to take questions.
Okay, thanks a lot, Harsh, for this. We had one question actually in the chat, which was related to the first part, but I think it came late, or I saw it late, which is from Shongshin, which is about how to measure the sublimation in situ. So that's the first question. So I suggest maybe you answer this one because it's for the first part, and then we see other questions.
Sure. So maybe I quickly go back to the slide where we tried to we tried to show the different mesh methods to measure sublimation. In this study, we used eddy covariance method, where we are measuring 20 hertz wind speed and 20 hertz water vapor to estimate sublimation. There are also gravimetric methods where you basically put the snowpack or allow the snowpack to be built on a scale, and then you measure the weight of the snowpack. That's the gravimetric method. This is a bit tricky to install and maintain over winters, and also you have a lot of lateral snow. And then there are modeling methods such as aerodynamic profile method, Bowen ratio, energy flux. There have been studies showing comparing all these different methods, and they agree, or at least this study agreed, that eddy covariance was the most direct way. So we used eddy covariance data to estimate sublimation in our case.
Okay, and maybe a follow-up question from Andy Hudson. Just a second now, it was gone. Can we have some comments about sublimation of wind-blown snow?
Hey, Andy, thanks for this very tough question. Uh, the so for this piece of work, we try to quantify sublimation from surface, so surface snow sublimation. For wind blowing sublimation, this is something we have also thought about a bit. We typically need these flux towers at different heights to try to quantify the boundary layer processes at different layers. But I think with Thomas Koibet now working with you in Svalbard, we will be able to quantify, or at least we'll give some number for blowing snow sublimation with Alpine 3D.
Okay, we will wait for this. We have another question in the chat from Konstantis. Thanks for the presentation. Another question again about sublimation. Based on the interesting data you shared, would we then expect marginal and ephemeral snowpack types to have more sublimation, since they are isothermal for the better part of their lifetime with many accumulation melt cycles?
This is a very good point. I think yes, in short. marginal snowpack should have more sublimation, also because they are more present in high energy system, and with marginal snowpack, ground heat flux can actually make the snowpack isothermal very early, as you already suggested. I would expect higher sublimation rates. What I didn't share in this presentation is another ongoing work with a colleague from Morocco, Nadia Rao Shati, where they have a flux tower in the Atlas Mountains. And over there, we also calculated sublimation fluxes, and we actually saw much higher sublimation in the Atlas compared to the Swiss Alps. And the Atlas are much more marginal snowpack. So I think I would definitely agree with you that marginal snowpack should have higher sublimation. Unfortunately, we have only limited data in these regions which are dominated by marginal snowpack to really try to quantify this more accurately.
Okay, thank you. And another question in the chat by Anna. Thank you very much for the presentation. At the Weißflugjoch, or in general, are there data sets that relate sublimation, wind speed, and show height or SWE?
So yes, we have. So Weißflugjoch is one of the oldest monitoring site, and we have all these measurements. So we have, other than the flux tower, we also have full all components to measure the surface energy balance. We have wind speed measurements co-located with our flux tower. We also have SWE, snow height measurements. Every, I want to say 10 minutes, but maybe an hour, and SWE measurements done every day. So we, interestingly, at Weißflugjoch, because it's such an old site now, and it's run by people who are interested in snow processes. We even found literature going back to 1946, where they tried to estimate sublimation for a week, and we compared our values. And ballpark, we were very close to 1946 conditions in 2024-25. So we do use all meteorological drivers, and this interest in Weißflugjoch on sublimation goes back really decades or maybe centuries.
Okay, thank you. And we have another two questions in the chat, and then we have someone, Fatima raised her hand. So first of all, Fahima is asking, is there any remote sensing based method to evaluate this sublimation loss? There will be refreezing occurring along with sublimation over the glacier surface. So how to incorporate them?
That's a good point. To answer your main question, can we measure sublimation with remote sensing? So far, not, but there's a good news. There's another project started recently called Snow Shifts. It's led by Francesca Kosch from Austria, and they are using satellite gravimetry to estimate sublimation. And I saw some first results where it actually kind of works, but it's still very early because to have these huge scales, it's also very so it's not there in any satellites so far. And to your other, so there is a potential, but I don't think there is any satellite right now which can tell us how much sublimation loss has happened. So one does it through an energy balance snow model, and then trusts that the model does a good job, which we saw in our case that they do not really do a good job. And to your other question about refreezing occurring on sublimation, that's a good point. We have refreezing, and then we also have condensation at night. So we have water vapor loss from the snowpack during day, and then water vapor going back into the snowpack during night. So we accounted for this. So what we reported at Weißflugjoch was really the net sublimation. So so accounting for nighttime condensation, and this would also happen in glaciers and on seasonal snowpacks.
Okay, thank you. So another question in the chat before we go to Fatima from Katarina. How can you separate sublimation from evapotranspiration or evaporation from the ground During, for example, melt season, when part of your flux footprint is maybe not fully covered with snow anymore.
That's a very good point. We have thought very hard and long about it. Uh, so what we tried to do in Weiss Fliok was be very conservative. So we defined our snow sublimation period from the time when snowpack was above 15 centimeter in November, and we cut off when the snowpack was at 60 centimeter. So we really had a very conservative cutoff. And this cutoff was based on the fact that we also have cameras there. And once we saw that the rock starts getting exposed, we said that uh, we don't really know if the latent heat fluxes come from rock evaporation or sublimation. So we said we cut it off. We keep our assumptions on the or sublimation estimates on the conservative side. So that's about when the ground is not snow covered. So the way we tried to do this was in the footprint of the flux tower. We really tried to find conditions when we can even find like an exposed surface, and then we said, okay, we cut it off. To separate transpiration from sublimation, this is another very interesting question. I try to find in literature how people do it. Nobody reports this, so it's a kind of a tricky topic. What we tried to do here, we found some lab experiments from the 1990s where people were trying to estimate transpiration rates at very low temperatures, air temperatures. And we found this relationship that below 5 degrees Celsius, daily average temperature, transpiration became negligible, at least in the species they were studying in the lab conditions. So in our study, what we tried to do was we have snow surface temperature and air temperature measurements, and we did a daily moving average, and we said that once we reach 5 degrees Celsius, we do not consider the latent heat fluxes as sublimation after that, because there is no way for us to tell if it's transpiration or if it's sublimation. So we have thought about this quite a bit. So our sublimation estimates are probably on the more conservative side because we just didn't know how to disentangle transpiration with sublimation. One of the ideas which we have and we want at some point to work on uh, is to use sap flux measurements along with our eddy covariance flux towers to try to remove the effect of transpiration. But that's something hopefully we'll be able to do in the future.
Thank you. Fatima, I will give you now the floor. So I put you on the stage. And
So,
you can unmute yourself. Yes.
so you hear me?
Yes, Fatih, we hear you clearly.
Yeah, thank you. Thank you, Harsh, for the presentation. Just a question about the shortwave and net radiation. I was wondering that, okay, we saw a very positive trend that the sublimation peak primarily with this shortwave radiation. And when we have, for example, high snow cover, we expect to have less shortwave net radiation. And then I was wondering that, does it mean that we have this sublimation peak at late season when we have very patchy snow, or it is because of, or perhaps because of the top of canopy shortwave absorption?
That's a good point. Thanks, Fatih, for that question. So, to first question about, uh, or the second question about canopy interception and that sublimating. So this is the Weiss flea oxide. It's above the tree line. Also, the spatial footprint of the flux tower is really above the tree line. It's at 2,600 meters. And when we saw that radiation was important in our analysis was during this period in mid of April 2025, and the snow height then was about 1 point, yeah, don't quote me on it, but more than a meter. So the ground was really snow covered, and we don't have canopy effects there because it's above the tree line. We have grasses, but the grasses are covered within the snowpack. So I don't think we have this interaction with long wave radiation on the canopy surface just because we are way above the tree line. But this canopy interaction effect in our global sublimation, we try to compensate a little bit for it. It's a bit hard because one would need leaf surface leaf temperature, which is not really measured during winters. So we
Mm.
tried to make some assumptions about this, like how does the canopy, because the canopy absorbs or it reduces the albedo spectacularly. And so in canopy dominated regions, the calculations become a bit more tricky. But this was not a problem we faced in Weissflur because it was about
Mm.
the tree line.
Okay, then that was interesting that is although we have a snow cover, then the short wave radiation was kind of high, yeah. And I
Mhm.
do think that if we, for example, plot it in a way that that we can see that the percentage of a snow covered, this would be maybe interesting. I don't know that whether to see that there is a difference and how this
Yeah,
is
we
coming.
also, what I didn't show here was in the global flux tower analysis, we also did MODIS-based snow cover because initially we wanted to look at some
Mm.
kind of a satellite measure of snow cover. Unfortunately, it didn't really work well for us, and I don't have that figure in this presentation, but we tried to show that MODIS systematically uh, overestimates the snow coverage. So when our
Mm.
short wave, we use directly albedo as a proxy for snow, which
Yeah, actually, yeah, that was another for me. But another, we have nowadays, I think Landsat and Sentinel kind of covered together to have a like almost daily crowd free.
Mhm.
So maybe that would be better than Modis, perhaps. Yeah, maybe. I don't know.
I think that's a good point.
Yeah. So thanks a lot, Ash. It was
Thanks.
very interesting.
Thank you, Fatime. We have actually two other questions and not so much time left. So first of all, again from Andy, um, is your lumped groundwater model agile enough? I think the stream data suggested faster return to base flow and so higher K values. Can you comment on any need for seasonal changes in the groundwater?
Thank you, Andy, for this very good question. I was waiting for an opportunity to talk about this. We tried to, for the we different the reason for having two groundwater boxes was we have a faster groundwater reservoir where we conceptualize the storage discharge relationship as an exponential function, and the exponent we got after calibration was about 1.5. So we needed, so in principle, the isotopic time series are lag or very damped. Streamflow is very flashy, and you need to generate flow from groundwater. So the only way we were able to conceptualize this was using an exponential storage discharge relation or nonlinear storage discharge relationship within one of the groundwater boxes. Without this, it doesn't really work. The isotope simulations are just very bad. So this was important. To your other point on if the groundwater parameterization should change over the season, I've not tried it. Would be interesting to try, maybe also in Scott Turner Breen. This is the kind of model structure I had in mind also for Scott Turner Breen. Would be interesting to see if changing this parameterization improves our results.
Thank you, Harsh. Just very shortly, the last question from our colleague Roman. Thank you, Harsh. You told about sublimation, but this is mostly from the snow surface. Is there any method how to estimate sublimation inside the snowpack, since it is a very important process for the growth of faceted and depth hoar crystals? Thank you.
Thanks, Roman. This is another very difficult question. We have thought a little bit about this so sublimation itself could be quantified into turbulent transfer, which is more governed by how much wind we have, so how much turbulent boundary conditions we have. And the second is via temperature diffusion within the snowpack. So by measuring temperature within different layers of the snowpack, we can quantify how much sublimation happens because of diffusion. And this has a very strong implication for snow microstructure. And this is something which one of our colleagues, Shakir Dar, is working on uh, to try to quantify this temperature-driven sublimation versus boundary layer sublimation. So that's my short answer. There also Shakir would be a good person to talk with about this. And I also think if anyone has more questions, because we are almost out of time now, you feel free to reach out to me on this email. And in chat, I quickly saw Melanie Barron's question on vapor. What is needed to determine vapor pressure gradient? Answer you very quickly. You need snow surface temperature. If you don't have snow surface temperature, you can still estimate it if you have outgoing long wave radiation. But write to me, I'll share the scripts how we do this.
Yes, sorry, Melanie, I missed your questions. Very sorry. So thanks a lot, Harsh, and thanks everyone for participating. So just one short note. So the next monthly webinar will actually not be in July, so not in 1 month. It will be in August. And it's our colleague Perti Alaaho who will be presenting. And we will announce more details soon on the website and also on Cryoscope social media. Also, the recordings of the webinars are now available online on our Cryoscope YouTube channel. Yeah, thanks a lot, Harsh. So this webinar will also be soon on the YouTube channel. So thanks a lot, Harsh, for presenting, and thank you everyone for attending this. And I hope we see each other soon during other occasions or during the next webinar at the end of August. Have a good day or evening, everybody. Bye.
Thanks, everyone.